A satellite is a body which is continuously revolving around our planet. Example, Moon. There are artificial satellites which are fixed on its orbit. It requires centripetal force of attraction between the satellite and our planet. So that satellite orbit in a circular path 24/7. Due to the gravitational force of attraction, the body which is revolving around our Earth is provided by a velocity v. That means a particular velocity is imparted to the body or satellite such that it can revolve around our planet continuously. That velocity is called orbital velocity. Orbital velocity can be defined as the velocity which is given to the artificial satellite a few hundred kilometers above the Earth's surface so that it may start revolving around the Earth. So let us consider a satellite in a circular orbit of radius capital R plus h from the center of the Earth, where capital R is the radius of the Earth and h is the height of the launching pad, or we can say height of the space station from on the Earth's surface. And if m is the mass of the satellite, then v is the speed given to the satellite. Then the required centripetal force which make the satellite continuously revolving around the Earth is expressed as the product of mass velocity squared divided by r plus h. That means it comes from the expression of centripetal acceleration force mv squared by r. So v is capital V and r is what? It is r plus h, where r is the radius of the Earth and h is the height of from the Earth's surface. So since the centripetal force is gained by or due to the gravitational force, we can write the expression of centripetal force is equal to the gravitational force experienced by the satellite. So this is the expression of centripetal force, that is m v naught square, where v naught is the orbital speed divided by r plus h, and it is the gravitational force of attraction between the Earth and the satellite. So g gravitational constant, mass of Earth, mass of satellite divided by r plus h square. From this equation we can obtain the expression of orbital speed g capital M by r plus h. So as the value of h increases, v naught decreases because denominator term increase, so v naught decreases, and for h equal to 0, that means for value of h very much less than the radius of the Earth, we can consider h is equal to 0. In that case, the expression of orbital speed is equal to gm by r, or this expression can be represented by acceleration due to gravity. So it is small g by gr. So v naught is equal to under root small z product of radius, or we can say v naught is equal to product of gravitational constant, mass constant, and divided by r. From this expression, these two expressions, we come to know that the orbital speed of the object to be orbiting around the planet is independent of the mass of the satellite. Whatever is the mass of the satellite, it is less important compared to the gravitational constant, mass of the Earth, and r. So from this two expression we can say that orbital speed is constant for any type of satellite. For any satellite having different mass, we can impart same speed so that the satellite orbit start orbiting around the planet. Since satellite orbiting around the Earth, we can say that satellite covers a certain distance. So what is the distance covered by the satellite is equal to the circumference of the orbit. So circumference can be represented by twice pi r, that is twice pi product of radius of the orbit. And here radius of the orbit is r plus h. So from this we have distance covered by satellite, and we come to know the orbital speed of the satellite. From these two informations we can find out what is the time taken by the satellite to complete one revolution, or what time will take by satellite to complete one revolution. So time period can be expressed as the circumference of the orbit divided by orbital speed. So it is twice pi r plus h divided by v. So so time period is expressed as twice by r plus h by v. So h is the separation from Earth's surface to the satellite, and r is the radius of the orbit, v is the orbital speed or orbital velocity. So on putting expression of velocity, here we have this expression, and on squaring both sides we have the time period square by constant and r plus h square. For h, that means separation from Earth's surface to the satellite, is very much less than the radius of the Earth, then we can write an expression of time period as this. So t squared is directly proportional to r cube, cube of the radius. From here we can say that square of the time period of revolution is directly proportional to the cube of the radius of the planet. So t squared is directly proportional to r cube for h very much less than radius of the earth, or we can say for negligible height of the satellite we can write this expression. For a satellite very close to the surface of the earth, h is equal to 0. So from this expression we can write time period. Expression for time period is equal to t equal twice by under root r plus r by z. Z is the acceleration due to gravity of the earth. Also from this equation we can find out the height of satellite. That means the separation between the satellite and the earth surface. So it is t squared, this value. So here we have given cube to this side, so it is cube root of this is a constant value. Here time period may be varying, so we can write h is equal to z r squared t squared by 4 pi square 1 by 3 minus r. So this is the expression for height of the satellite. Nowadays, large number of artificial satellites are launched and in day to day. So they are used to find out the weather forecasting, for communication purpose, for tracing precious metals and oil below the earth's surface, to study various phenomena connected with sea, to study various phenomena in the outer region of the earth's atmosphere. So some of the satellites revolving around the earth, and it takes a time period of 24 hours. That means our earth also takes 24 hours to complete one rotation. If the time of rotation of earth and the revolution of satellite is 24 hours, that is equal, then we can say the satellite is a geostationary satellite or synchronous satellite. Geostationary satellite we can say like this, because or stationary means fixed. Okay, so how can we say a fixed when it is revolving? So because when the time period of satellite as well as the rotation of earth are equal, it appears like the satellite is fixed in a position. So this is relative compared to earth and the satellite, so we can say it is a geostationary satellite. For a satellite to be geostationary, it must follow some conditions also. um, it should be at a height of 36,000 kilometer above Earth's surface or equator. The plane of the orbit of the satellite must be perpendicular or normal to the axis of rotation of Earth. So the satellite should orbit around the Earth from west to east, as does the Earth. Let us now find out the expression of energy associated with the satellite. There is a motion of satellite with velocity, that is orbital velocity. Therefore, there is a kinetic energy associated with the satellite, and due to the configuration of the satellite and the Earth, there is a gravitational potential energy also with the satellite. So let us write the expression for both kinetic and potential energy. So this is the expression of kinetic energy, half m orbital velocity squared. We have put the expression of orbital velocity, so kinetic energy expression become product of gravitational constant, mass of the earth, mass of the satellite divided by twice r plus h, where h is the height of the satellite from the earth's surface and r is the radius of the earth. So let us consider gravitational potential energy at infinity be zero. Okay, so we have considered gravitational potential energy at infinity be zero. So the potential energy at distance r plus h, that means the potential energy at distance r plus h is that is from the center of the earth, u equal to minus z capital M small m by r plus h. Therefore, the total energy expression is the sum of the kinetic energy plus potential energy. So let us put these expressions here. So is r plus h by multiplied by 2 minus z capital M small m r plus h. So total energy is equal to, it is minus z capital M small m by twice r plus h. So this is the expression of total energy associated with the satellite. So here it is energy term, but here is a negative sign. It is of great importance. This negative sign shows that the satellite is bounded to the earth. Again I repeat, this negative sign shows that the satellite is bounded to the earth. That means satellite revolves around the earth. Otherwise, if the total energy have positive value, then the object escaped to infinity. That means flew out due to the centrifugal force acting on the body or satellite. So it escaped from the earth's gravity. So this negative sign is of great importance. If energy have positive value or zero, then satellite would not be bounded to the earth. And here we have considered that the satellite are always at finite distance. Therefore, this energy comes out to be negative or minus z capital M small m by twice r plus h. So the energy with a positive sign cannot express the energy of a satellite.